All right, guys, this video is going over types of chemical reactions, okay? Um, the five kind of basic types of chemical reactions and how to balance chemical reactions or chemical equations. It doesn't have to be a chemical change, it could be a physical change, but how to balance chemical equations and how to look at a chemical equation and decide what type of chemical change is taking place, what type of chemical reaction is taking place. So, in your visible learning, this is 6-1 and 6-2. But yeah, let's just dive into it, and should be pretty easy. It just takes some memorization, as usual. All right. So the first thing we're going to do is we're going to talk about the types of chemical reactions, and then we're going to talk about balancing them. All right. So let's jump into it. So there's five standard types of chemical reactions: synthesis, decomposition, single replacement, double replacement, and combustion. Now, within some of these, we have different types. So like there's double replacement, formation of a precipitate, double replacement, acid base neutralization. There's also something called oxidation reduction reactions, which most of these reactions, not all of them, but most of these reactions can also be categorized as redox, oxidation reduction. So this is not the only way to classify different chemical changes, different types of chemical reactions, but these are kind of the five broad types of chemical reactions. And within each of these categories: synthesis, decomposition, single replacement, double replacement, combustion, we can have subcategories of them, right? But these are the main ones that we're going to be looking at. Okay. Um, some quick things: synthesis and decomposition are essentially opposites, and combustion is going to be the easiest one to identify because we're really only going to be talking about combustion of organic compounds, so like hydrocarbons or alcohols or something like that. So this is going to be real easy to spot because it's going to be some kind of organic compound plus oxygen, and the products are always going to be CO2 and H2O, so carbon dioxide and water. So those are the ones that are easiest to classify, but it turns out they're the most difficult to balance. All right, but let's go ahead and jump into it, and let's go through each type. All right, so synthesis. Basically, you're looking at a synthesis reaction when you have only one product. So two things form one thing. Basically, that's what you're looking for. So A plus B yields AB, right? And it could be two elements make a compound, like hydrogen and oxygen yield water. This would be a synthesis reaction. But it doesn't have to be two elements making a compound. Just as long as you have one thing, one compound on the product side, it's probably going to be synthesis. Okay, so here we got two different compounds making a single compound, so this would also be classified as synthesis, right? So we have sodium oxide and water form sodium hydroxide. But again, you just need to be able to look at this and go, oh, okay, that's a synthesis reaction, right? Basically, it's following this simple pattern, okay? So again, decomposition is the opposite of synthesis. So one reactant. If you only have one reactant, then it's got to be decomposition. And so again, it's just we were flipping the arrow. So instead of A plus B yielding AB, it's AB yields A plus B, right? And so again, it could break down into, it could be a compound breaking up into the elements that make up the compound, right here. So here we have sodium oxide yields sodium plus oxygen, okay? But it doesn't have to break down into just elements, right? Here we have H2O2, so this is hydrogen peroxide, forming water and oxygen, so a compound and an element. But again, we just have one thing on this side of the equation, so we should be thinking decomposition, okay? One thing to note is we've already looked at equations that kind of look similar to this, but understanding right now we're focusing on chemical reactions, not necessarily physical reactions. So when we have a solid ionic compound dissolving in water, remember we wrote equations like this way back in Unit 4. But understand, dissolving is a physical change, not a chemical change. So if you solve this, this would not be called a decomposition reaction. This is just, a salt dissolving in water. Sometimes it's called a solution reaction or a dissolution reaction or a dissociation, but it's not decomposition, right? For this to be decomposition, you would have to have the elements of the compound over here. And notice, like, it's just sodium ions, chloride ions. If this were decomposition, it would have to be sodium, not +1, just neutral sodium, and then Cl2 because it's diatomic. Okay, so just watch out for that. That's not a decomposition reaction. This would be the decomposition reaction, right? Because this is not an ionic compound dissolving. This is an ionic compound decomposing and forming its elements. So that would be decomposition. This one up here would not be decomposition. Okay. All right, so what about single replacement? All right, so something's got to be replaced, and single replacement means one replacement. So this is the kind of pattern you're looking for. A plus BC yields AC plus B. And so kind of looking at the pattern, you have B paired up with C, A comes in and replaces B, now B is by itself, and A is paired up with C. So A replaces B, but nothing else is replaced, so that's a single replacement, all right? And so what you're really looking for is an element in a compound on this side of the equation and an element in a compound on that side of the equation. So if it's element compound yields element compound, that's probably going to be a single replacement reaction, okay? Now, how to determine what's going to replace what and all that stuff, well, we'll get to that when we get to 6-4, predicting the products. But the rule is like replaces like. So if A is a metal, then it's going to replace a metal. If A is a nonmetal, it's going to replace a nonmetal. A halogen replaces halogens, stuff like that, okay? And a main thing to note for single replacement reactions, whatever gets replaced, whatever ends up being by itself over here, is in its elemental form. Okay, so A is an element over here, but in this compound, it's most likely an ion, right? B is an ion over here, probably, because it's in a compound, probably an ionic compound, but again, most likely it's an ion over here. But B over here is not B in its ion form, it would be B back into its elemental neutral form. Okay, so whatever gets replaced is now in its elemental state. That's going to be key. All right. So here's a simple single replacement reaction. You have lithium and sodium chloride yields lithium, chloride, and sodium. And so you notice lithium's over here, the element lithium, the metal, and it replaces sodium, the ion, right? This is not sodium, the metal, this is sodium ion, because it's in sodium chloride. And now lithium is now paired up with chloride. It is now an ion. This is a lithium ion. But the sodium is no longer an ion. If it was an ion, I'd have to write Na plus here. But remember, whatever gets replaced is in its elemental state, so this is just neutral sodium. Okay? But again, lithium replaces sodium, single replacement. Okay? Here we got fluorine replacing chlorine, but really it's fluorine replacing chloride. This is Cl minus. So fluorine, the element, replaces chloride, the ion. The fluorine becomes fluoride, the ion, but notice the chlorine becomes chlorine, the element, not Cl minus, but Cl2 gas, Cl2, okay, the element chlorine, right? But again, just one replacement, single replacement. And again, like replaces like. So here, the metal replaced the metal. Here, the halogen is replacing the other halogen, okay? So here we have sodium and HCl, hydrochloric acid, yields sodium chloride and hydrogen. Again, element compound, we should be thinking single replacement. And if you look at it, sodium is replacing H plus, right? So think of hydrochloric acid as H plus and Cl minus, right? Sodium comes in and replaces H plus, and now sodium is now +1 paired up with chloride, and the hydrogen is now in its elemental state. The hydrogen is no longer H plus, it's just hydrogen neutral, but remember hydrogen is diatomic, so if hydrogen gets formed as an element, it's going to be H2, okay? Another thing to kind of note, as we're looking at these reactions, I'll scroll back a little bit. Notice like this reaction isn't balanced, okay? This reaction isn't balanced. This reaction isn't balanced. Right now, we're just focusing on classifying the reactions. And we'll talk about how to balance them later. So again, here, not balanced, okay? But we'll talk about it, all right? So double replacement, now you're looking at compound plus compound yields compound plus compound. So we get two replacements. So if we look at this pattern, A is replacing C, but C is replacing A, right? So A and B are paired up and C and D are paired up. Now on this side, A is paired up with D, but C is paired up with B. So A replaces C, but C replaces A, double replacement. Okay, so how is this going to differ between single replacement? Single replacement, remember, was element in compound, yield element in compound. Here we're looking at two compounds yield two compounds. That's going to be the main difference between single replacement and double replacement. Okay, so let's look at it. So here we got silver nitrate plus sodium chloride yields silver chloride plus sodium nitrate. So notice the sodium and the silver replaced each other, right? So sodium's paired up with nitrate and silver's paired up with chloride. So this would be a double replacement reaction, okay? Notice nothing is in its elemental state. These are all ions, right? These are all ionic compounds. So this is a silver plus 1 ion, this is a nitrate 1 minus ion, sodium 1 plus, chloride 1 minus. And over here, it's silver 1 plus paired up with chloride 1 minus, sodium 1 plus paired up with nitrate 1 minus, okay? So if we look over here, we got potassium and barium switching places. So now potassium's paired up with nitrate on this side, and barium is paired up with sulfate on this side. And one thing I want you to notice here, and this is going to be important when it comes to balancing, but also when it comes to predicting the products later on in the unit, is that notice like it's K2 over here, but the subscript for potassium over here is 1, right? Nitrate, the subscript for nitrate is 2 over here, but the subscript for nitrate over here is 1. And the reason that is because these are ionic compounds, right? They're based on the charges. Potassium is 1 plus and nitrate is 1 minus. So when potassium and nitrate pair up, it's going to be a 1-to-1 ratio. Barium is 2 plus, sulfate is 2 minus. So when they pair up, it's going to be a 1-to-1 ratio. Okay, so don't just let the subscript of the ion on this side tell you that that's going to be the subscript of the ion on this side. It really depends on the charges and what the ratio is going to be when they pair up. So watch out for that. So again, this reaction is not balanced, but these are the correct formulas of the products. And so you'd have to go back and adjust the coefficients to balance. Okay. So a way to think about double replacement reactions, you can say the cation switch places. You could also say the anion switch places. Usually we say the cation because that's always written first in the formula. But the charges of the compounds that are formed still have to add up to 0. So you still got to do the crisscross to get the right formula of the compounds on this side. Okay. So over here we got lead 2 acetate and hydrochloric acid. The lead and the H plus switch places. So now you have lead 2 plus paired up with chloride. That's why it's Cl2 over here. Notice it's just Cl over here. The reason why there's only 1 chloride paired up with 1 hydrogen is because hydrogen's plus 1 and Cl is minus 1. So that's a 1-to-1 ratio. But now when chloride pairs up with lead 2 plus, because the lead is 2 plus and chloride's 1 minus, you have to have 2 chlorides for every 1 lead. So you get PbCl2. And notice you get H plus paired up with acetate, just 1 acetate. And the reason that is because acetate's 1 minus and hydrogen is 1 plus. So it's a 1-to-1 ratio. So again, just because acetate had a subscript of 2 on this side doesn't mean it's going to have a subscript of 2 on this side. It might. It just depends on what ion it's pairing up with. But again, this is just a case of a double replacement reaction. And again, it's not balanced. We'll get to balancing later, but these are the correct formulas for everything. Okay. So acid-base neutralization is also a kind of specific type of double replacement reaction. So if I have an acid and a base, remember a base right now is just anything that has hydroxide, so ionic hydroxide, and H in front. This is nitric acid and sodium hydroxide. But again, think double replacement. Sodium pairs up with nitrate and H plus pairs up with hydroxide, H plus and OH minus, right? So you end up with sodium nitrate and you end up with HOH, which is water. So When an acid and a base neutralize, you remember you always get water. Usually the two products are a salt, an ionic compound, and water. Okay. All right, so again, combustion is going to be the easiest to spot. It's always going to be something burning in oxygen. So you're going to have an organic compound burning in oxygen plus oxygen, and the products are always going to be CO2 and H2O. Now, technically, it's only CO2 and H2O if you have something called complete combustion. All right. We're just going to assume complete combustion all the time. Now, if you have incomplete combustion, another byproduct is going to be carbon monoxide, right? That's why, like, if you're burning gasoline, you don't want to do it in a closed environment because the burning of gasoline isn't complete combustion, it's incomplete combustion. So you don't just get CO2, you also get CO, and too much carbon monoxide can be deadly. So you want to watch out for that. But right now, we're just going to always assume complete combustion. So you're looking, if these are your products, most likely combustion. And again, you're looking for organic compound plus oxygen yields CO2 and H2O. So here we have benzene plus oxygen yields CO2 and H2O. That's a combustion reaction. Here we have ethanoic acid plus oxygen yields CO2 and H2O. We would still call this combustion, right? So combustion of a hydrocarbon, combustion of an organic acid, but still organic compound plus oxygen, you're thinking combustion, and it's always going to produce CO2 and H2O. So again, combustion reactions are going to be the easiest ones to spot. They're going to be the easiest ones to predict the products because the products are always going to be CO2 and H2O. But they're kind of difficult to balance. Like if we were looking at this reaction, like how are we going to balance this? They're a little bit more difficult to balance, but there's a systematic way to do it. All right, so we'll get to that. All right. So, and again, combustion just means burning in oxygen. Okay. All right. So now let's talk about balancing. So when you balance, I kind of just like to go back and forth, except if it's a combustion reaction. If it's a combustion reaction, I use a systematic process, which I'll show you in a second. But you just go, from one side of the equation to the other side of the equation, and you just adjust your coefficients. You can't change the subscripts. The subscripts are what make the formula the correct formula, right? So the formula, like sodium chloride is NaCl. You can't change the subscript. You can't call it Na2Cl. You can't call it NaCl2. Sodium chloride is NaCl. Water is H2O. You can't, if you have water in the equation H2O, you can't all of a sudden change it to H2O2 and change the subscripts because that changes the substance, right? And then the final thing is you always need the lowest whole number ratio of coefficients for your balance. And sometimes, all the coefficients being 1 is balanced. 1 is kind of understood, but be careful in a Schoology assessment, if you have to type in the coefficients and there's a blank in front of it, you're going to have to type in 1 if the coefficient's 1. But for the most part, if you're just handwriting a reaction, a coefficient of 1 is understood, okay? And so a way to think about the yield sign is it's an equal sign. So the stuff on this side has to equal the stuff on this side in terms of mass, in terms of matter. So the number and types of atoms on this side have to equal the number and types of atoms on this side. But I can't change the subscripts, okay? So because hydrogen has a subscript of 2, because oxygen has a subscript of 2 here, I can't all of a sudden make this a subscript of 2 over here because that would change this to hydrogen peroxide and it would no longer be water. So you can only adjust the coefficients. So this is what I like to do. I like to just go back and forth, one element to the other, right? Or one ion to the other, right? Depending on what you got. So here I got 2 hydrogens and over here I got 2 hydrogens. So I don't need to adjust anything yet, right? But then if I look at oxygen, I got 2 oxygens, but I only have 1. So what do? I put a 2 in front of the water. If I put a 2 in front of the water, the coefficient gets distributed through the whole thing. So I would have 2 times 1 oxygens on this side. So 2 oxygens on this side, 2 oxygens on this side. So right now, putting that 2 there balances my oxygen. But what did it unbalance? It unbalanced my hydrogen. Now I have 4 hydrogens, 2 times 2 hydrogen on this side, but I only have 2 there. Well, that's an easy fix. Just put a 2 there. And that would be the balanced equation. 2, 1, 2 would be my coefficients. That's the balanced equation. Okay. So let's look at this one. Okay. So I got 2 sodiums, but I only have one sodium on this side, so that's why I put a 2 here. All right. All right. I have one oxygen plus one oxygen, so I have 2 oxygens on this side. And now that I have a 2 here, I have 2 times 1 oxygens on this side, so I have 2 oxygens. So now I'm looking at this equation. 2 sodiums, put a 2 there, and now I got 2 sodiums. 2 total oxygens on this side, 2 total oxygens on this side, 2 hydrogens on this side, and because I have that 2 there now, 2 hydrogens. So this would be the balanced equation, 1, 1, 2. Those would be my coefficients. Okay, let's keep going. Let's look at this one. So here we got sodium oxide yields sodium plus oxygen. So here, 2 sodiums but only 1 sodium, so I got to put a 2 there. Okay. But now, as I'm looking here, the sodium's balanced. I got 2 sodiums, but only 1 oxygen, 2 oxygens. So I got to come back here and put a 2. So I put a 2 there to balance my oxygens. 2 oxygens, 2 oxygens. But now, putting that 2 there, now I have 4 sodiums and only 2 sodiums on this side. So now I got to adjust. Okay? So my final coefficient over here, I got to change this to a 4 to make the sodium balance. So 2, 4, 1, that would be those would be my coefficients for that balanced equation. Okay. All right, so here we got hydrogen peroxide yields water and oxygen. So 2 hydrogens, I'm not going to change anything yet. 2 oxygens, 3 oxygens. Oof, what am I going to do? Well, let's put a 2 there and make this 4 oxygens. Now, if I made that a 2, that means I have, if I made that 4 oxygens, but it also made me have 4 hydrogen. So I got to put a 2 in front of water to get 4 hydrogen. But now that I have a 2 there, I have 2 times 1, 2 O's plus another 2. So I have 4 oxygens on this side. And putting that 2 there gives me 4 oxygens on this side. So that would be my balanced equation. Okay. So here, just kind of more balancing. You can see I had to put a 2 there and a 2 there to balance the sodium. Again, a lot of students see the Cl2 over here and they just want to put a 2 here. But you know sodium chloride doesn't have a subscript of 2 for the chloride, so you can't change that, right? It's just the coefficients. Okay. So here, notice this one's all balanced with 1s. So 1, 1, 1, 1, right? Sometimes you don't have to change the coefficients, right? Sometimes it's all balanced with 1s. That's okay, right? And so again, a lot of times kids are tempted to put a 2 there and a 2 there, or to forget that fluorine and chlorine are diatomic when they're elements, okay? But all we have to do to fix this is put a 2 there and a 2 there, and now everything is balanced, okay? So 1, 2, 2, 1 for the balanced equation, all right? All right, so now let's look at some double replacement reactions. They can get a little complicated, especially when you have these polyatomic ions to deal with. But I think the best way to deal with these is think of these as one thing. If you see SO4 on this side and you see SO4 on this side, if you see NO3 on this side and NO3 on this side, and those subscripts didn't change, it's just the subscripts outside the parentheses might have changed, then don't treat this as 1 sulfur and 4 oxygens. Treat this as 1 sulfate, right? Don't treat this as 2 nitrogens and 6 oxygens. Treat this as 2 nitrates. So let's go back and forth. 2 potassiums, 1 potassium. Okay, so notice I had to put a 2 here so I could get 2 potassiums. Now notice that doing that, now let's keep going down the list. So my potassium's balanced with a 2 there. Now let's go to sulfate. I have 1 sulfate, 1 sulfate. I don't have to adjust anything. 1 barium, 1 barium. I don't have to adjust anything. 2 nitrates, and because I put that 2 there, 2 nitrates. So the nitrate's balanced. All right. All right. So again, it's easier to treat acetate as one thing. So you have 2 of them here, right? So up here I have 2 acetates, but over here I only have 1. so I need to put a 2 there. All right. One lead, I don't need to adjust anything. One hydrogen, okay? But now because I put that 2 there, 2 H's, so I got to put a 2 here. Now I have 2 chlorines, right? So that is my balanced equation, all right? So what about combustion reactions? They can be kind of the more difficult ones to balance. Here are the steps. Balance the carbon and the hydrogen first. Go to the product side and add up all the oxygens. Divide the number of oxygens on the product side by 2. That's going to be your coefficient for oxygen. On the reactant side for the O2, and then make whole if needed. So I'll show you an example, right? So here we have a combustion reaction, right? Hydrocarbon plus oxygen yields CO2. So the first step is balance the carbon and the hydrogen first. So I got 3 carbons, so I put a 3 in front of the CO2 to get 3 carbons. I got 8 hydrogens, so I put a 4 in front of the water. 4 times 2, that's 8 hydrogens. Now I'm going to go to this side of the equation and add up all my oxygens. I got 2 places where I have oxygen. So I have 3 times 2, I have 6 O's here, and I have 4 times 1, I have 4 O's here. So that's a total of 10 oxygens on this side. So what we're going to do is divide that number by 2, that becomes 5, and that's going to be my subscript for the oxygen here. Because if I put a 5 there, 5 times 2, I got 10 O's on this side, 10 O's on that side. All right, so there you go. So 1, 5, 3, 4, that would be my balanced equation. Let's try it for the benzene one, okay? So again, here's my combustion reaction. First thing I'm going to do is balance the carbon and the hydrogen. So 6 carbons, I got to put a 6 here for the CO2, okay? 6 hydrogens, I got to put a 3 here for the water to get 6 hydrogens. So notice that puts me here. Now I'm going to add up all the oxygen. 6 times 2, I have 12 O's here, and 3 times 1, I got 3 O's here. That's a total of 15 oxygens on the product side. I'm going to divide that by 2. That's 7.5. That's going to be my coefficient for O2. Okay? So this equation is balanced. It's just not properly balanced. To properly balance, you got to get rid of any decimals or fractions. So how do we get rid of 7.5? We double every coefficient. So if I double this, this was 1, so now it's a 2. Double this is a 15. I double this, that's a 12. And I double that, that's a 6. So this is my final balanced equation for that reaction. Okay? All right, so hopefully that helps you with classifying and balancing. It just takes a lot of practice with balancing, but once you get the hang of it, it's pretty easy. You just go back and forth, adjust your coefficients. And if you change one, then you might have to go back and change another one. So just, so balance with pencil, because you might put in a 2 or a 3 as a coefficient, and then all of a sudden adjust something on the other side of the equation, and then you got to come back and change the coefficient that you just adjusted. So just go back and forth until everything's balanced, and you're good to go. All right. Have a good one.